All right, question 6 says, find a vector equation for the line of intersection for the planes x minus z is equal to 1 and y plus 2z is equal to 3. Okay, and you see the planes up here, and these planes intersect in a line, you see in yellow. I'm going to refer to this line of intersection as L. And our job is to find a vector equation that describes the points on this yellow line of intersection. Now, you have to remember from section 12.5 when we discussed lines in R3, there are two key ingredients in describing a line. Okay, and those are a direction vector, so in other words, a vector parallel to your line, and a point on your line. Okay, so we have to use the fact that this line L is the line of intersection for these two planes to extract those two key ingredients, right? We need to find a direction vector and a point on the line in order to write this vector equation. All right, so let's go ahead and begin. I'm going to start by considering the normal vectors for these two planes. Okay, so n1 is the normal vector for the purple plane, n2 is the normal vector for the green plane. And the key observation here is that since the line L lies in both planes, right, because it's the line of intersection, both of these normal vectors are orthogonal to the line L. And so the cross product vector, as you see here in red, that, well, we know is orthogonal to both n1 and n2, and so it must then be parallel to the line L. Okay, so I'm going to go ahead and compute this cross product. Now, n1, that's again the normal vector for this purple plane that's described by the equation x minus z is equal to 1. And to find a normal vector to this purple plane, I can simply read off the coefficients of x, y, and z in its equation, right? So 1, 0, negative 1 are the components of this vector n1, right? Notice here you don't see a y in the equation. So put another way, the coefficient of y is 0. So again, 1, 0, negative 1 are the components of n1. Likewise for n2, well, the components will be 0, 1, 2. Okay, again, you don't see an x in the equation, so the coefficient of x is 0. So 0, 1, 2 are the components of the normal vector n2. And if you take the cross product, you're going to wind up getting 1, negative 2, 1. And again, this vector you see here in red, the cross product vector, this is a vector that is parallel to our line L, and so in turn, it's a direction vector for L. All right, great. So now how about a point on this line of intersection? Well, for that, we want a point that lies on both of these planes. Okay, so in other words, we want an XYZ triple that makes this purple equation and this green equation true. Okay, so in other words, we want a solution to this system of equations. Now to make things simple on ourselves, let's go ahead and set z equal to 0. So in the first equation, that forces x to equal 1. And in the second equation, that forces y to equal 3. And so we find that the point P with coordinates 1, 3, 0 is a point on the line L. Okay, so again, the coordinates of P, 1, 3, 0, satisfy both the purple equation and the green equation. So this point P is on both planes, and so it must be on this line of intersection. Cool. So now we have a direction vector for the line of intersection, and we have a point on the line of intersection. And so, going back to section 12.5, when we discussed lines in R3, this was the general form, right, for a vector equation for a line, right? And here, x0, y0, z0, those are just the coordinates of a known point on the line. Okay, so what about the ABC? Those are the coefficients of the parameter t in these equations here, and they are the components of our direction vector. So you put that all together, and you get 1 plus t, right? So x0 is 1 plus at, that'd be just 1t. That's the I component of our vector equation. And then y0 plus bt. Well, that's going to be 3 minus 2t. That's the j component of our vector equation. And then lastly, z0 plus ct, that's just going to be t. That's our k component. And that will do it. All right, great. Thank you so much.